Good afternoon and welcome to today's PSDI webinar, Trusted and Reproducible Workflows for Machine Learned Interatomic Potentials. My name is Dr. Mansoor Nelikal, Community Coordinator for the Physical Sciences Data Infrastructure, PSDI, and I'll be chairing today's session. Now let me introduce our speakers. It's now my great pleasure to introduce today's speakers, Elliott Kasoar and Dr. Alin-Marin Elena. Elliott Kasoar is a research software engineer in data-driven materials and molecular sciences group at STFC, where he leads the development of digital infrastructure for machine-learned interatomic potential as part of the PSDI Data to Knowledge Pathfinder. He's also pursuing part-time PhD at the University of Cambridge, focusing on ML potentials, usability, and performance benchmarking. Dr. Alin-Marin Elena is a computational scientist at STFC and leads the data-driven molecular and material sciences group at STFC. He is a major contributor to open source scientific software such as CP2K, DL Poly, AAC, and janus-core, and leads data to knowledge pathfinder within PSDI. His work spans machine-learned interatomic potential, computational statistical mechanics, HPC, and reproducible scientific workflows. About today's talk. In this webinar, Elliott and Alin will explore the recent advances in machine-learned interatomic potential, introduce software frameworks, including janus-core, aiida-mlip, and MLPEG. With that, I'll hand over to our speakers, Elliott and Alin. Over to you.
Thank you for the kind introduction. So Happy New Year to everyone. I appreciate that you came directly from holiday and started to attend the webinar. Today we will speak about the latest development, data to knowledge pathfinder, and we'll concentrate mainly on the trusted and reproducible workflows for machine learning interatomic potentials. The work, it's in main core of this work, it's funded by PSDI, but there are other funding streams that contribute to this, like CSP5 and MCC and the Ada Lovelace Center, that in general is the place where we use a lot of the things that we developed in PSDI for real-life applications. Okay, so will be a talk of two people. I will start myself and I introduce data to knowledge pathfinder and what we do into it, a little bit of janus-core, and then Elliott will take over and present you the PSDI repository for data to knowledge, the aiida-mlip, ABCD, and then at the end he will speak about MLPEG, which is a framework for benchmarking and validation of various machine learning interatomic potentials that we developed and he develops as part of his PhD. And then I will finish with future work. Let's start by thanking people. So these are in general people who helped us to the work that we do. Joe, Tamas, Elias, and Gabor in Cambridge around ABCD and about some of the workflows that we do around Maze. And Joe and Elliott work on the benchmarking and on MLPEG. Harvey from Queen Mary University, he's a contributor to various projects that we discussed today, mainly janus-core. Scott Woodley, who is the chair of MCC from UCL, helped us mainly in testing. He offered us his group as, let's say, testers. Carlos Bornes, he contributed to janus-core. He's from Charles University in Czech Republic. And Kiran from Harris from Manchester University, he spent a small internship with us and he contributed to janus-core. And of course, the other people from STFC, Jacob and Federica, who are part of the team. Federica left for Italy. Jas, who is in another pathfinder in the biosimulations once, but for part of the repository work, we work together with them. And some of the graduate students, Mohsin, Jessica, and Cameron, who played with various aspects of the project. Data to knowledge. What is the data to knowledge pathfinder or activity? We all know machine learning. Everything is about machine learning, and I'm doing materials modeling. So the idea is, how do we get all this landscape together? So the machine learning usually needs to start from some data or some database. Of course, in our field, a lot of time misuse the term of database. And there are various applications of machine learning that are relevant to us in materials modeling. Mainly, you can build models based on papers, on various input files, output files of codes. You can curate, you can throw an LLM at them, and you can create your expert advice bot, your ChatGPT specialized for your domain. We are not going to touch this area in this pathfinder. There are other projects where we are looking. We developed one which is called Goldilocks. Here, if you are interested, we can discuss later. One more common approach is you start with a structure, you have a potential energy surface associated with that set of structures, and you can train a machine learning interatomic potential on it. Once you are happy with it, you can start doing modeling as before. There is the aspect where you do not want to have a potential energy surface, you want to jump directly to properties. You have some computed properties, you train a surrogate model on them, and you predict properties for materials which are not your training set. This is a quite nice field that a lot of people who do data science are interested in. A lot of times in material science, people are not very happy with the accuracy of the results, so there is a lot of work that can be done there. And of course, there is the other, when you start with experimental properties, you build a form of surrogate model, inverse surrogate model if you want, and then you can extract the structure out of it or other properties. This is practically what AlphaFold does. And of course, there are other branches which are a little bit more niche that help with various things in materials modeling, but we will not discuss here. So for this talk, at the moment, we concentrate on second top branch, how we get from structure to machine learning interatomic potentials, and what infrastructure we need to get something that we can trust. Okay. So current aim of the pathfinder is to design and deploy infrastructure to host training data for machine learning interatomic potentials, including the potentials themselves. As features, we want to be able to curate, store, distribute, and interrogate MLIPs and training data. Visualization and training workflows. So we are still far from visualization. We are the beginning of that. Training workflows, we are working on some area to show you. Benchmarking and validation, which is very important. I mean, are the potentials that we produce useful for the simulations that we want or not? And this is what the MLPEG tries to answer. HPC integration, and of course, nothing is good if you do not do training to train the new generation and to upskill the current generation on using these things. We start with the training, so we are running together with colleagues from universities. We are running this school on chemistry and materials machine learning. This is happening this year in Dalsbury. It's the third edition. It's an international school. There are around 40 participants that we select every year from the applicants. And the topics that we cover are from general ML. The applications all are materials and chemistry. From general ML, LLMs, property predictions, Bayesian optimization, generative machine learning interatomic potential is just a small chapter into this school. And this is really organized in collaboration with the community. We have various sponsors. PSDI is one of them, Alchemy Hub is the other, CCP5, SECAM, and this year CCP5 and CCP9 and SECAM, and this year we have sponsorship also from Psyche. What is the state of the art when it comes to machine learning? In general, you will get something which is a leaderboard. I'm still using the MadMesh Discovery leaderboard. There are a few others there you can use. In general, all of them will suffer more or less the same benefits and issues that I will explain about this one. One, they tend to be a lot of potentials that you can see, which is nice because 2 years ago when we started, there used to be 4 or 5 of them. Now there are plenty of them. And since the beginning, there are two kind of groups of people interested in potentials. One were people interested to materials discovery, and this would be the left-hand side part of the graph, this of the table, where the potentials are listed in a certain order. But if you are a physicist, usually you are not interested in that. You are interested in how well your potential can do to some well-defined physical quantities. In this case, for example, you can order them by this column KSRME, which tells you how well they do predict phonons, to predict energies and forces that gives you good phonons. Okay, and you see that the order changes. Okay, there are a few things you should keep in mind here from this. Is the data that is used to train these potentials, and you see a lot of them from the good ones on both sides. They use this collection of OMAT 24 Alexandria database and MP-Trash, it's a collection. You see more data, they tend to be better. With a few exceptions, majority of the potentials found in these foundation models, they start from here. And the other thing you should try to have a look is the number of parameters. Okay, so in general, potentials who tend to do better, there are potentials who have a lot more parameters. There is another issue. This started as a kind of community exercise, but a lot of people from the community, they kind of stopped submitting the tests for the benchmark here. So you will find, probably if you are interested in the field, you will find, potentials, which you will not see in this table. And this is mainly because the authors stopped submitting. Even the one that I'm more involved with, like MACE, except the first generation, we never submitted anything again to this one. So be very careful when you see these tables that they don't tell you the full story. Foundation models, so they tend to be pretty good. So some years ago, we came out with this MSMP, Gabor Jani and his group came out with this, and then we spent a lot of time trying to benchmarking to see how good it is for various physical and chemical problems. And then at the time I was playing with MOFs, and we could see that it was doing quite well. Do the CO2 physisorption in one of the MOFs that we were interested. Then, of course, when you started to look a little bit more in detail, that we realized that it's not doing as good as we expected. If we wanted to see the more subtle physics, like density of states, for example, we realized that the potential itself was missing a lot. You can see here. So then the fine-tuning was invented, and you can see how you can improve the potentials. And here in the archive paper, you can look, if you are interested, to look in the second generation of MSMP. So the field is moving a lot. It's very promising in moving the modeling field forward, and practically we just added a new way of being able to model in between classical force fields and more expensive DFT or quantum chemistry methods. Of course, one thing that I said before, if you can still remember, the data is important. While majority of the data that you need for simple machine learning interatomic potentials are energy, forces, stresses, sometimes even not the stresses, and these tend to be a small amount of numbers. We download them from various places. Materials project of Alexandria or Meta puts there on Hugging Face. There is another set of data which is more interesting for people who are interested in beyond machine learning interatomic potentials, to advanced machine learning models, or to do molecular property predictions. It's the electronic structure. And Meta spent a lot of computational time creating a data set of more than 100 million molecules, and they made available the electronic structure data. Unfortunately, only a subset of the 100 million is available, where they have more than, like, the electronic densities, orbitals, multiples, things that you can use for more advanced things. The only place where you can access it until recently was in Argonne. Unfortunately, if you want to download it here, it will take you quite a long time. So I managed to mirror it in UK via PSDI, and at the moment we can access it only via API. So if you are interested, please contact me. Then our infrastructure, of course, we need to design it. So from the start, policy with our design is to be a separation of concerns. We do not want to deal with things that other people can do. We don't want to reinvent the wheel, so we need to use things as much as possible that other people did. So we are building a lot on janus-core. We'll see later, it's built on top of IC. aiida-mlip, the workflows are built on top of AIDA, developed in PSI. The databases we use ABCD, Optimate, things that the community already has. We didn't start writing everything. Users are important, so you need to develop infrastructure, being it even digital, with the people who use it in mind. And always we looked at people. Users are coming at different abilities, so you will have a casual user. Probably you will need a web UI where they can access things easy without too much specific work to be done, preparation to do the calculations. Then you may have intermediate users that can run everything in a Jupyter notebook or Marino notebook these days and things like that. So we have to cater for them too. And of course, you have the expert users that they do not need any of this. They are happy with a command line interface. They are happy with REST APIs and other APIs. So you have to cater for them too. Okay. Continuous deployment. So every bit of infrastructure that we do is continuously tested and deployed. So practically, if somebody wants to use what we are doing, can just go to the GitHub repository, clones, and it can start. So we are making our best to be sure that every single commit we put is tested and can be used. Extensible is Python-centric. It allows fast development with relatively decent speed for what we do. Keep in mind the majority of the hard work is not done by us, but is done by separate packages. Okay, it's open source, BSD free close, so everybody can just use it regardless whether they are academia or industry. And we concentrated on early adopters, and from the beginning we had few groups who got to test things early with all our stuff. In the ecosystem, there are few things that we will discuss about. It will be the repository, the janus-core, the aiida-mlip, and the benchmarking, which will be the more important things. I will start with janus-core, and then Elliott will take over and will speak about the rest. So janus-core, what is janus-core? Is just an aggregator of various machine learning interatomic potentials and various methodologies of modeling that you use. So in such a way, when you want to try, you don't have to start to set up your own, build your MD or see how to do the funnels and things like that. At the moment is used, to my knowledge, by around 10 groups or more in counter group in UK and abroad. Believe in this GitHub statistics, we have 42 stars there. Some of the groups that use it, we work together with them. We offer them one-to-one help. But there are people who use it without totally independent of us. Okay, and as features, we integrate practically almost all the machine learning interatomic potentials that you saw in that table and few more. Unfortunately, I didn't update the slide. So practically, you can have the maze, you can have the original CGNet and M3GNet, the LineF7Net, Nekip Allegro, and then the Facebook, for the commercial ones from Orb. The Mattersim, Isen, and UMA, the last two are Mattersim comes from Microsoft, Isen and UMA come from Facebook. Okay, what you can do with each of these potential, you can do single point, you can do geometry optimization, you can do equation of state, you can do phonons, you can do descriptors, you can do elasticity, and you can do run molecular dynamics. There are a few very simple workflows that you can use. You can do nudge elastic bands. You can do rare event simulation by integrating with Fluent. Okay, and of course you can use Janus to do training and fine-tuning. There is a little bit of result analysis, but in general we do not try to reinvent the wheel. There are a lot of packages that can do the post-processing after that. So if you are an experimentalist, probably you want to do use something like MDance, or you can use something like MD Trash or whatever, what people do. It's integrated with various other components. aiida-mlip is the main one, the workflow engine that we have for these things. And of course, it's part of the PSDI and MBCD. One plan that we had in mind was to put active learning into Janus, and then during the thing I started to change my mind about that, and the active learning, since it's depending what type of systems you are doing, can be a little bit quite system dependent. We decided to move it into the workflow part. So we have all the tools to do the active learning, but you will have to write a workflow to do whatever active learning protocol you are interested in. The technology is Python. We have proper unit testing, leaking, documentation, and automatic publishing. We have a Zenoton integration. If you are interested in how much carbon producing by running your machine learning calculations, you can use Code Carbon. We use a typer for the command line interface, and as a package manager, we use everything. It's running automatically. We use it not only for, let's say, research purposes in various projects here, and people use it, but we use it as an engine for to deliver training. Documentation and tutorials are very important, so we have an entire section on our website. You can go directly there where you have various tutorials. Tutorials are available in two flavors, via Python or via command line interface. We try to keep them relevant all the time, so they tend to be automatically run when added to the documentation of the code. You can run them directly via cloud in Google Colab. You just click, you go to tutorials, you will see there is a button and you can click. Via SDFC Jupyter Hub, we use them for specific trainings, and we offer Docker and Podman containers with Jupyter Lab and Marimo if you want to play by your own and to run on your own machine. So up to now, we use it to deliver training at UCL, for MCC, and this part of CSP5 and the CAML schools. The other thing that we started doing, this was a graduate student project. We tried to look at various ways to create a simple graphical interface, a web graphical interface where people can upload their CIF, and when they hit a button, they choose a model, they hit a button, and they get their geometry optimization. This is the project, Cameron's project, that we played around. Then we find out that Facebook published something similar, so we are not totally mad in doing. Now we are looking at various alternatives and see if we can do all these nice things via aiida-mlip, rather than building specific services for things which are, let's say, computational memory intensive. Okay, so I will stop here, and Elliott will take over for the rest until the conclusions.
Okay, so I'll start by talking a bit about the PSDI repository. So, as Alin mentioned earlier, one of the key aims of our project was to be able to store any data relevant to our community, so it can include datasets, publications, models, and workflows. And so the way we can do this is through the PSDI data collections in the repository. So you can see a screenshot of sort of what it looks like on the right-hand side. We have, there's two different communities currently set up. There's one for us and there's one for the biomolecular simulation community. And each of those communities has its own domain-specific metadata. So you can store some relevant information about your specific dataset. So for example, in this case, we're saying that this dataset contains information about energies, forces, stresses. You might want to store the number of structures, number of elements, so you can ultimately be able to query this data and find it more effectively. Currently, we don't have DOI minting, but that's hopefully coming soon, and similarly for cross-search integration. So it'll be much easier to find relevant data for your needs, integrated with the rest of the PSDI ecosystem. As well as the web interface, we also started to develop, in collaboration with a biomolecular simulation pathfinder, in particular JAS API, so we can more automatically and pragmatically interact with this repository. So rather than having to go to the web interface, we might want, for example, to upload results of a simulation, say from janus-core. We might want to be able to upload that automatically. And so we built this package, which you can find a data collections API. So we can firstly just create a template metadata file with all of the sort of information you might need. We can do validation of metadata files. So if you have your own, or if you customize for the template, then you can check that it's still valid against the schema. And finally, we can upload this data, the metadata, along with relevant files, and create an example, an item on the repository. And ultimately, yeah, as I said, this should be integrated into janus-core in the future once it's all finalized. Functionally, it's all there, but we're working on the final stages of documentation and testing. And I have a quick demo. Okay, so this is using our command interface. So here we firstly create this example YAML file and just show you what it looks like. So in this case, we define the access, we define the custom fields. In particular, this is where we would define our community-specific metadata. We want to save files, and then most of the bulk of the relevant information is this section of metadata. So for example, you would write down your affiliation, your name, any identifiers. So for example, linking to ORCID, and you can attach various other things like the rights, the license, and other tags. In this case, I've actually already created a slightly more detailed example, which I've called demo.yaml. So over here, so for example, we have some of our community-specific metadata. In this case, similar to what I showed earlier, I've got the number of atoms, I've got single configuration, calculation level, some of my information, and we can also do some tags. So for example, if it comes from MD, you can have it as a subject thing and it'll appear. We can check that it's valid, and hopefully it should be. And then finally, we can upload it using, again, the command interface. In this case, I'm uploading to the dev version of the PSDI data collections. You define where your metadata is, you define your API key, a set of files. This would be a glob of files if you want to do multiple ones. And we select for communities. In this case, I've selected data to knowledge. You could also do the permanent simulation community, and it will automatically populate the relevant metadata for it. And then if we then go to website, we can see communities. So we have multiple communities, but data knowledge is one uploaded to. So it doesn't automatically get published, it goes to requests, so it can be checked for and curated. And here we can see that it's created my example optimized MOF structure. It's added all of the relevant metadata, and it's added the keywords that I asked it to. And so we can edit this, or we can, if you could ask for it to be reviewed and published. Of course, you can also do all of this through the web interface as well. So you can upload the files. You can add all the information. In this case, there's quite a few things I didn't populate for this example, just for simplicity, but there's quite a few things we can add. And this is where you would add your community-specific metadata. So there's a few extra things which I also didn't populate, including the provenance. And this will probably be fleshed out over time. So currently, this is only sort of relevant for a single file. But ultimately, we'd like to be able to do this for multiple files. And so if you have a series of structures, you might want to label the number of atoms for each of those. But that's not available yet. Okay, down to workflows. So Alan talked a lot about how we would run calculations using janus-core, but in practice, a lot of the time you want to be able to build up workflows, potentially quite complex workflows involving MLIPs in various different ways. And to do this, as you mentioned earlier, we use aiida. So what this does is it sort of manages, it controls automated, fully reproducible workflows. And it does this, if you see on the right-hand side, it sort of tracks the inputs, outputs, and metadata in this provenance graph. And this is all stored, each of these nodes is stored in a database, so that can be queried. It can be shared and exported and used elsewhere. And this is an example of sort of a very high throughput workflow you might have. So you might start with a single structure, create a huge number of other structures and do some sort of filtering, and ultimately end up with a small set at the end telling you some interesting properties. In our case, because we want to run workflows involving MLIPs, we needed to add some custom data types to be able to store relevant data in the nodes. In particular, we added data types for Janus config files, so this makes it much easier to define all of the metadata we need to run a calculation and make sure that aiida passes it correctly. And similarly, we also want to be able to store the models themselves, and that wasn't available without our intervention. And finally, the bulk of the plugin we've developed is the calculations themselves. So essentially, all of the calculations and simulations that Alan mentioned earlier, we can run these using aiida. A couple are still in progress, and these are required because you need to be able to define exactly how, for aiida to track everything correctly, you need to define the inputs, what the process it's calling is, and what the outputs are for each calculation. So that's what we've done. But of course, we don't just want to run a single calculation, we generally want to run a series of calculations. And so we provide tutorials and examples of how to do this. Firstly, just actually tutorials of how to configure aiida, because one of the barriers a lot of people find with aiida is because it's so powerful, it's also quite complex to set up in the first place. You need to be able to create a profile, which is where all your data is associated with. You need to set up the code, so in this case, janus-core, as a sort of binary that aiida can run. And then you need to set up your computer. And in many cases, you probably want to be able to run things on a remote HPC system. And we have tutorials for how to do this. But then we also show how to then combine these different nodes in order to build up a workflow. So for example, we have an example of how to high throughput calculations. So you might want to do geometry optimization of a large number of structures. We show how to do this. And we also have a sort of a workflow builder to do this in a very automated way. And now more recently, we've been developing a series of fine-tuning example workflows. So these, I'll show this in a second, but essentially we want to be able to build up in various different ways new sets of data that we can add to fine-tune a foundational model. I will very briefly try to share this. So in this case, this is just an example of, it's using a relatively new, sort of last year or so, aiida has developed this work graph interface. And essentially each of these is sort of a task which is doing some sort of calculation or otherwise. And so you would define, for example, a task which is doing molecular dynamics. You would define a task which is doing the training, and you put these all together into a graph, which it automatically builds and connects all of the relevant bits of data. So here we define a bunch of inputs. We then some sort of molecular dynamic simulation. From this, we get a trajectory, which we can calculate the machine learning descriptors on, because these can be useful to do some sort of filtering. Because if we have lots of similar structures, we don't necessarily want to use all of them for our training. So then we take some subset of those, we run DFT to get the sort of reference energies, forces, and stresses which we need to do training. We create this training file, and finally we run fine-tuning using this subset of data from the molecular dynamics simulation. And so this overall it's a relatively simple workflow in terms of it's all very linear. But equally, it's combining quite a few different types of tasks. So it's not necessarily trivial to combine calculations from janus-core, calculations using Quantum Espresso, which has its own AIDA plugin, and some intermediate steps, which are sort of purely Python based. And we can also see this is sort of a full provenance graph that it also stores. So you have all of these inputs at the start, which are defining how it should run. And you see how each of the nodes is connected up. So we do this MD. From the MD, we take this trajectory, which feeds into a work graph, which does the descriptors, etc. So yeah, we're building up a series of these, and hopefully it's useful both as a demonstration of how you build up workflows, but also usually better to take a lot of these and use them in your own as you need to, more or less out the box. Okay, are we back to the presentation? On to something slightly different, ABCD. So this is about storing data, but also being able to sort of share and summarize it in a more effective way. So this is building on existing work from Revolutionize group. And so they had a MongoDB implementation of this, where you could upload it as a series of structures and try to understand the contents of those structures. And so sort of use case for this is perhaps more if someone shares some data with you, or if you were to download a data set from a repository and you want to understand what are the properties available to me, because that can be useful to understand what you're able to do with that data in order to use it for fine-tuning, that sort of thing. But the issue is MongoDB doesn't scale very well once you get to very large numbers of structures. So my work a couple of years ago now mostly was trying to replace this backend with OpenSearch instead, which is much more scalable. It's used for very large, generally text-based sets of data. And generally we found that for sort of queries of, I don't have a number here written down, but I think we've sort of found a 10-fold increase in speed for queries. And we can do quite complex queries in a few different ways. You can do, there's this query language called Lucene, which allows fairly simple, almost English-like queries. You can do, if you want to do sort of more advanced things, you can do sort of Python dictionary or JSON-like queries. And you can also do sort of much more complex queries using scripting if you need to do more complex things which aren't available through sort of simple things you'd be able to do, say, a SQL database. But yeah, this is useful because you can attach and ingest data with arbitrary information. That's very common in our field because you often have data labeled, say, with energies for multiple different references, and you wouldn't necessarily know which one is the relevant key, or you wouldn't necessarily know which ones are available to you unless you have this sort of mechanism in place. And finally, we're talking about MLPEG. So this is work that's both part of my PhD, as mentioned earlier, but also very much relevant to the interests of the project. And so the idea here, I'll show it live in a minute, is there's sort of a couple of main use cases. So firstly, you might be interested in developing a model and understanding when you make changes to the model architecture, has that actually improved physical predictions or not? Secondly, you might want to compare two different sets of or multiple models and understand which one is most well suited to my needs. And the issue with a lot of existing sort of leaderboards and tables is they tend to be fairly inflexible and fairly most often sort of specific to materials and bulk crystals and not necessarily relevant to a lot of people's needs. And so what we've been working on is sort of developing a much more general testing framework where you can sort of highly automated, highly customizable and hierarchical, so you can see at different levels of detail all of the information that's relevant to you. And also trying to build a much more diverse set of tests compared to a lot of testing suites at the moment. And then a big part of this is also visualization of our results. So be able to sort of intuitively explore the data and understand in different levels of detail exactly what's going on. And so there's sort of multiple different sort of use cases, I suppose, in terms of how you'd interact with it. So firstly, a lot of people will just go to the live website we're hosting, have a play with that, but you can also download Docker or Podman images and host it locally, and then you can make changes as they suit you, or sort of add your own changes as well. You might want to add to your local version, or you might contribute a new model. In that case, we have this fairly simple YAML file where we define essentially how to sort of load the model, and then a few extra sort of parameters which tell us how to add dispersion corrections for certain tests. And then the most common use case at the moment is adding new tests themselves, which we'd then want to run on all the different models that we're interested in. And this is sort of broken down into 3 main sections. And I'll probably actually start with the last one, which is the application, because actually, if you wanted to, you could skip the first 2 steps and go straight to the third one. If you just had the data in the correct form, in the correct place, you can define the interactivity you're interested in, and it will automatically add it to the app. In most cases, you'd probably go at least 1 step back and have the analysis, which is saying, having run some sort of calculation or simulation, how do I take that data and then calculate some sort of metrics which are relevant for your system? And this will become clearer once I actually show. But say, for example, you might be interested just in a metric might be the RMSE of the energy between your predicted energies from different MLIPs and from the reference DFT data, for example. And what we try to do here is make it as automated as possible in terms of generating, say, scatter plots, bar charts, visualizing the charts themselves. So we have a bunch of Python decorators where essentially if you build these functions in the analysis in the correct way, it will automatically generate all of the tables and plots that you need without having to sort of manually do this yourself, because a lot of this is similar between different tests. And then finally, there's the calculation itself, which is actually using these MLIPs in different ways. So this could be, in many cases, single points, but increasingly we want to do more complex things, so calculating phonons, doing MD simulations. And this is fairly backend agnostic. So we have some examples where we use janus-core, some are built using MLIPx, and some will be purely sort of Python ASC based. Okay, and finally, I will try to do a demo of this because it should be much clearer. There we go. Okay, so this is kind of our front page. So we have a summary of all of we group each test by category. So each of these tabs is a different category we tried to organize things by. And then this shows us our sort of normalized score for each of these categories when we get a final score at the end. But actually, for most people, you're not necessarily interested in an equal weighting of each score for every different test. You might be more interested in, say, molecular systems. And so we have this weighting where we can increase the weight and it will change how these different scores are weighted to suit your needs. But we can also look more specific, and you can of course reset things as well. Within each category, we can then also, we have this overall summary table, which is broken down by each test we have within the category. But you might be interested in looking at the specifics of each test and changing that to suit your needs as well. So for example, we have these thresholds, and these define whether what you consider to be a sufficiently good or bad score, so unitful value, based on your specific needs. In some cases, it might be that actually there's quite a large error, or you don't actually need a particularly accurate result. And then you can increase this and say, actually, it doesn't matter too much. I don't necessarily care as long as they're within half an EV. Probably not, but in some cases you might want to. And similarly, in some of the tests, we have multiple different metrics. So here we have, if I show the interactivity, we have a measure which is just the ME, but we also have a ranking error, which is telling you for each of these is actually the relative energy between different structures. And so what you might care more about isn't necessarily the mean, but whether it's ordering multiple structures' energies correctly. So you might want to increase the relative weight of that metric compared to this one. And then in general, we try to have sort of multiple levels of interactivity. So here we have a scatter plot, which shows all of the results, but you might want to look at a specific model. You might want to look at what is the structure that's giving this specific. We can also do slightly more complex visualizations. So for example, for the NEBs, we look at lithium diffusion, and you can see here, for example, this is a slightly odd NEB, but you can visualize sort of trajectories and understand what's happening at each stage of the trajectory. And we can also do very quite large structures as well. So in this case, you can see here, for example, some of these are really huge structures, and it's really useful to be able to sort of see what is it, why is this an outlier? What structure is it? And we sort of dig into the details. Okay, I think that's everything I had to say. The final slide is for Alan.
Okay, so these are various aspects that we are developing, a lot of them in collaboration with community. MLP, as Elliott said, is part of his PhD in Cambridge with Gabor and his group. As future work, we are looking in workflows deployment via aiida-mlip to make them a little bit easier for people to use, the extensions to the benchmarking framework. And of course, aiida-mlip, we can use the features for HPC integration. And data integration from community. So as I said, the MetaOmol 25 data set, we are hoping to be able to get the full electronic structure of 100 million molecules. UCL contacted us about making public some of his data via the repository and more. The same in Cambridge, we're looking in depositing some of the ML and the data into the repository, and various internal other Lovelace Center projects that we have in here that want to make data public. Data exploration, so this was the part of the visualization that we were interested. It would be nice to make it available on top of the repository via Nomad or Materials Cloud, whatever it's easier to integrate with an existing repository. We are looking LLMs for materials more in other projects than specifically in this one, but maybe of interest, the lessons that we learn there. And now, especially that with Omol 25 dataset, we will have a big dataset of other properties than just machine learning interatomic potentials. We are interested in models for properties prediction. And of course, always people ask to do more training. That is very important if we want to keep things moving. So this is all from us. Thank you, all of you, for attention. So compared with the olden days of potential development, how much time does one save with ML, I suspect? So my experience is majority of people, let's say normal users, shouldn't have to develop a potential from scratch. They should fine-tune on top of one of the foundation models. There are quite a few nowadays, and almost all of them offer various flavors of fine-tuning. And given that you want to concentrate on a relatively small problem, it can be something as short as few weeks, depending how good you are to do the reference data, the DFTs, or other quantum chemistry theory that you want. So yeah, as usually I'm saying that Gabor says years saved, I say PhD students saved. So in general, it's really much more streamlined these days.
I think that's all the questions. Thank you very much. It has been a wonderful webinar. Thank you for all the insights. Before wrapping up, I have a few updates. So our resources are live now. If you can see my screen, all these resources are available on the PSDI website. If you are new to PSDI, please take a look at our website. We have a lot of data sources, services, and tools which may help you in your research. We have some upcoming events which is given on our events page. Most importantly, there is a Chemicals and Materials Machine Learning School 2026, which has been described by Alin at the beginning of the webinar. So all the details are on our events page. The workshop is focused mainly on PhD students, in particular those in materials and molecular simulations field. Also note that all the previous webinars are available on our YouTube channel, so please do take a look. This webinar will be uploaded shortly. And that brings us to the end of today's webinar. Thank you again. Thank you all very much for joining us. And a big thank you once again for Elliott and Dr. Alin for a fantastic presentation. Wishing you all a great rest of the day, and we hope to see you at another PSDI event soon. Take care and goodbye.